Now, in the previous lecture we have derived the least square approximation using the coordinate functions phi x as polynomials or as orthogonal polynomials. Now, what we have written, let us just remember what we have done in the least square approximation. We have written the approximation P x as C 0 phi 0 x, C 1 phi 1 x plus so on C n phi n x. We have chosen these phi I x as simply equal to x I, or we have chosen phi I x as orthogonal polynomials. Then we have derived the constants C I such that the aggregate or the sum of squares of the errors or is minimized, and that approximation we call the best least square approximation, best approximation in the least square sense. We have derived the constants C I and we have also illustrated through an example, and let us now see illustrated through an example in the case when we choose them as orthogonal polynomials. And now, when if phi I x are the orthogonal polynomials, we have derived the values of the constant C I as integral a to b w x f x phi I x dx divided by integral a to b w x phi I squared x dx. Now, when the data is given, these integrations have become summations and we have certain equations, and we have illustrated examples when a data is given. Now, let us illustrate the case when the function given is a continuous function and we want to write a least square approximation for that. So, let us take it as an example. Obtain the least square approximation. For let us give the function as simply a simple function, let us take this on 0 1 using polynomials of degree 1 and 2, and secondly using Legendre polynomials of order 1 and 2. Now, we are formally going to define these polynomials later on. Let us also give the data here that is required for us. P naught x is equal to 1, P 1 x is equal to x, P 2 x is equal to 3 x squared minus 1, and W x is equal to 1 for the case of the Legendre polynomials. Now, here a continuous function is given to us. I would like to first of all approximate it by simply polynomials of degree 1 and 2. Then I would also do the same thing by using the orthogonal polynomials, that is your Legendre polynomials. Let us now first take the first part of it. Now, we need the linear approximation first. Therefore, we are writing P 1 x is equal to C naught plus C 1 x. And what we mean by least square is that we are saying that integral 0 to 1 f x minus C naught plus C 1 x whole square dx is equal to a minimum quantity. Now we get two equations from here by minimizing with respect to the parameters C naught and C 1. So, I will set delta I by delta I C naught is equal to 0. So, let us follow the entire procedure, even though we could have written the equation directly, let us just see how we every step we proceed on. So, I can now differentiate this 2 times f x minus C naught plus C 1 x dx is equal to 0. I have differentiated with respect to C naught. So, I have a minus sign which I removed that minus sign, we have a minus sign coming that I have cancelled it throughout. I can cancel 2 also from here. So, what I have here is C naught integral 0 to 1 dx plus C 1 integral of x dx, and this is equal to right hand side 0 to 1. I would now substitute the value of f x given to us, f x is equal to x cubed here. Now, I integrate, this is simply gives us x between the limit 0 to 1, I get 1, therefore, C naught x square by 2 within the limit 0 to 1. So, I will get 1 by 2, this is x to the power of 4 by 4 within the limit 0 to 1. So, I will simply get 1 by 4. So, the first equation reads C naught plus C 1 by 2 is equal to 1 by 4. Now, let us take the second parameter, that is delta by delta C 1 is equal to 0. So, I will get 0 to 1 2 times f x minus C naught plus C 1 x into, I differentiating with respect to C 1, I will get minus x over here dx is equal to 0. Now, again we retain the terms of C naught C 1 on the left hand side and take f x to the right hand side. Therefore, I would get C naught integral 0 to 1 x dx plus C 1 integral 0 to 1 x square dx, on the right hand side 0 to 1 x cubed into x, that is x to the power of 4 into x. Integral of x gives us x square by 2, that will give you C naught by 2. This gives x cubed by 3, that is C 1 by 3, x to the power of 5 by 5. So, I will have 1 by 5. Therefore, let us rewrite the equations here, C naught plus C 1 by 2 is 1 by 4. Let us take 2 multiply by 2, that is C naught plus 2 by 3 C 1 is equal to 2 by 5. Now, I can solve it easily, I can subtract and find C 1 and substitute it over here, and what I get C 1 is 9 by 10, then using this I get C naught is equal to minus 1 by 5, substitute it here and get this result. Therefore, our polynomial approximation, least square approximation is equal to C naught plus C 1 x. So, I can take 10 common out and write this as 9 x minus 2, that is 1 by 5. So, I will have 9 x minus 2. This is the least square linear polynomial approximation. Now, I would like to know what is the total error that is committed here. So, I can also find that. So, I can call this as least squares error, and that will be equal to integral of 0 to 1 f x minus C naught plus C 1 x, that is 1 by 10 9 x minus 2 whole squared dx. This error was minimized, and we are now finding out what is this minimum error that has been committed. So, I can just integrate this and obtain the value of this and say that this is the least square error that has been committed in this particular approximation. Now, we have been asked to find the quadratic also. So, let us do the quadratic approximation. Quadratic approximation. Now, in this case we are taking the polynomial approximation as we add one more term to the previous case, that is your C 2 x squared, C naught plus C 1 x plus C 2 x squared. Therefore, the first step would be to define our least square approximation 0 to 1 f x minus c naught plus c 1 x plus c 2 x squared whole squared dx is equal to minimum. Now, in this case what we have done is that we have added one more term here. Therefore, everywhere you will get an extra term. We in fact, without writing any further step, we can write from this case what will be the equations from here, because there will be one more term here C 2 0 to 1 x square dx, and there will be here C 2, and there will be one more term, one third equation also would be there. Therefore, we will get 3 equations which we can write immediately by setting delta by delta C naught is equal to 0, and this gives us, let us write down straight away, that will be C naught integral 0 to 1 dx plus C 1 integral 0 to 1 x dx plus C 2 integral 0 to 1 x squared dx, and on the right hand side we have 0 to 1 x cubed dx. That is C naught into 1, this is x squared, and this is x cubed dx. Therefore, this is C naught, this is C 1 by 2, x cubed by 3, that is C 2 by 3, the right hand side is 1 by 4. Now, if I set delta by delta C 1 is equal to 0, now I will have a product with x here, I will have x square here, I have x cubed here and x to the power of 4 here. Therefore, we would simply get C naught by 2, C 1 by 3, C 2 by 4, this is x cubed, therefore x 4, this is x 4, therefore I will have 1 by 5. And the third equation gives us delta I by delta C 2 is equal to 0. Now, when I differentiated this with x C 2, I am getting x square here in the product. So, the leading term will be x square, x cubed, x to the power of 4, x to the power of 5. Therefore, this will be C naught by 3 because of x squared, x cubed, therefore, C 1 by 4, this is x to the power of 4, that is C 2 by 5, and this is x to the power of 5. So, I will have 1 by 6. Now, this is a simple solving the system. So, we can solve this system and then substitute these values in P 2 x, that is C naught plus C 1 x C 2 x square, to get the quadratic approximation in the least square sense. We can similarly find out the least square error by substituting the values of C naught, C 1, C 2 in this expression and get what would be the minimum error that would be committed in the least square sense. Now, let us go to the second part, that is in terms of the Legendre polynomials. In terms of Legendre polynomials. Now, let us just remember that the orthogonal property of Legendre polynomials are minus 1 to 1 p m x p n x dx is equal to 0 for m not equal to n, and 2 upon 2 n plus 1 for m is equal to n. So, this is the orthogonal property of the Legendre polynomials. Now, one very important thing that we remember is that the Legendre polynomials are defined over minus 1 to 1, but the problem here was given in 0 to 1. Therefore, we must change given interval. If it is a b, we reduce it to minus 1 to 1 by using a linear transformation. So, I will first reduce this into minus 1 to 1 and then go and write down the least square approximation in terms of the Legendre polynomials. We use a linear transformation, We will write down some x is equal to A t plus b. So, let us write it at A t plus b. Now, what is it we want? We are given the interval 0 to 1. So, therefore, when x is equal to 0, I need t is equal to 1. The lower limit for t should be 1 when x is equal to 1, and when x is equal to 1, I want the upper limit to be 1. Therefore, 0 to 1 we are now bringing to minus 1 to 1. We shall do the same thing if arbitrary interval is given, some p q interval is given, we shall use the same transformation and then find out the values of a and b. So, let us substitute it over here. Therefore, 0 is minus a plus b, and x is equal to 1, that is equal to a plus b. So, if I add, I get 2b is equal to 1 or b is equal to half, therefore, a is equal to half. Therefore, the transformation is x is equal to half t plus 1. If you want to look what is t, t is equal to 2x minus 1. Therefore, from here we can write down now what is our function given to us. So, the function f x is equal to, let us call it as a function as g t is equal to x cubed, that is 1 by 8 of t plus 1 whole cubed, and now the interval is in minus 1 to 1. The interval for t is minus 1 to 1. Now, the least square approximation shall be written in terms of Legendre polynomials in the variable t, because we want the approximation over this interval. Therefore, we write down the least square approximation p 1 of t is equal to c naught p naught of t plus c 1 p 1 of t, where we remember p naught is equal to 1 and p 1 is equal to t. Therefore, this is our approximation, f x is f of t is approximated, or f x is equal to g t, that is approximated by this one. Now, we have derived earlier the expression what will be the, in the case of the orthogonal polynomials, the values of the constants can be directly written down from here. So, I can use this value by putting I is equal to 0 and so on, and find out what will be the values of these parameters. So, let us write down, substitute it here. So, I will have here c naught will be equal to integral a to b, weight function is 1, our variable is t now. Sorry, I will replace this minus 1 in the next step. So, this is w x is 1, f x is equal to 1 upon 8 t plus 1 whole cubed, phi 0 is p 0 dt divided by a to b 1 p 0 square dt. Let us now translate it correctly as minus 1 to 1, 1 upon 8 can be written outside, t plus 1 whole cubed, p naught is 1. Now, the denominator is minus 1 to 1 p 0 square dt, and we would like to use the orthogonal property that we have just now described, that minus 1 to 1 m n is equal to 0, therefore, this is equal to 2. So, this gives us p 0 square, this is equal to 2, when n is equal to 0 we have 2 here. Therefore, what we have here in the denominator is 2. Therefore, I just open it up and integrate this, integral minus 1 to 1, I can take this as t cubed plus 3 t square plus 3 t plus 1 of dt. Now, t cubed is an odd function, therefore, its contribution is 0, t is an odd function, its contribution is 0, therefore, only t square and 1 will contribute the solution. So, this is 1 by 16, that is 3 into t cubed by 3, 1 by 3, and t cubed within the limits minus 1 to 1, that gives us 2. Then integral of 1, that is t, that gives us 1 plus 1, that is equal to 2. Therefore, this gives us 2 plus 2 4, that is equal to 1 by 4. Now, let us write down what is C1. C1 is integral of minus 1 to 1 by 8 t plus 1 whole cubed into P1, P1 of t is t dt, in the denominator minus 1 to 1 into P1 square of dt. Now, minus 1 to 1 P1 square dt, that is 2 upon 2 n plus 1, therefore, 2 upon 2 plus 1, that is equal to 3. Therefore, the denominator the value is 2 by 3. Therefore, this we can write it as 3 by 2 and this is 8, that is 16, 3 by 16, and let us open this up, that is your t cubed plus 3 t square plus 3 t plus 1 into t dt. Now, we are multiplying by t, therefore, this is odd function t cubed and this is t, this is an odd function, therefore, the contribution of these two will be 0. So, we will have contribution only from these two. This is t to the power of 4, therefore, 1 by 5 into 2, this is 3 t square, that is 3 into 1 by 3 into 2. So, I can cancel off this, this is 10 plus 2 12, therefore, 3 by 16 into 12 by 5, that is equal to, I can cancel off 4 from here. So, 9 by 10, 9 by 20. Therefore, we obtained the value of C1 also. So, let us substitute and get down what is our approximation. This is equal to C naught P 0 of t plus C1 P 1 of t. C naught is 1 by 4 plus C1 is 9 by 20 into t, or simply 1 by 20 into 5 plus 9 t. Now, I can go back and then find out what is in terms of x also. So, I can just substitute what is now t, value of t we have written as 2 x minus 1 is the value of t. So, I can substitute the value of that. So, 5 plus 9 into 2 x minus 1. So, this is equal to 1 by 20, that is 18 x, this is minus 9. So, I will have minus 4. So, I will have here 1 by 10 9 x minus 2. Therefore, the linear approximation in terms of the orthogonal polynomials turned out to be the same as what we have done in the other case, when we have done it directly using the polynomial approximation of order 1. So, we have got the same result over here by using the orthogonal polynomials also. Now, let us do the quadratic also. So, I would now write down the quadratic approximation. Therefore, I will now write down f x is approximately, that is g t, that is equal to C naught P naught plus C 1 P 1 plus C 2 P 2. They are all in terms of t and t lying between minus 1 to 1. Now, as in the case of the polynomial approximation, what we have here added is only C 2 P 2 we have added. Therefore, in a sense what we are doing is a correction to the linear approximation that we have performed. Therefore, the values of C naught and C 1 is going to the same, because when once you use this approximation and then write down this formula, that C naught C 1 formula, it is going to the same. Therefore, we need to find only C 2 to get the quadratic approximation as an extension of the linear approximation. So, I need only to find C2 to get our result. So, I can now write down my C2 from here as -1 to 1 1 by 8 t plus 1 whole cubed. Now, I have the P2 is equal to, now we have written here the expressions for P2 is given in our problem. P2 is equal to 3 x square minus 1, variable is t now, this is 3 t square minus 1. So, I will have to use the value of P2 as, let us put a bracket here, 3 t square minus 1 dt divided by -1 to 1 P2 square dt. Now, the denominator value, we know the value of this -1 to 1 P2 square dt is 2 upon 2 n plus 1, n is 2, that is 4 plus 1, that is 5, 2 by 5. Therefore, this will be simply 5 by 16, this is 1 by 8 outside. So, I will have -1 to 1, I can open it up as t cubed plus 3 t squared plus 3 t plus 1 multiply by 3 t square minus 1 of dt. I will leave this for you to this, the value of this comes out to be half. Therefore, the approximation GT is equal to C naught that we already obtained as 1 by 4, C1 is 9 by 20 into t plus half 3 t square minus 1. If I want to convert it back to x, yes, I will substitute t is equal to 2 x minus 1 and write down the approximation in terms of x as 1 by 4 plus 9 by 20 into 2 x minus 1, 2 x minus 1 plus half 3 into 2 x minus 1 whole squared minus 1. Therefore, we can see the advantage of using the orthogonal polynomials, that we are able to obtain these parameter values C1, C0, C1, C2, Ci directly, and then it is a matter of simple integration to perform and get the values. And the advantage that we mentioned was that there is no ill-conditionedness if you use this particular format, whereas if you use the polynomial approximation and if you go to higher order approximation, say 5, 6, 7, 8 like that, then there is a chance that these these can become ill conditioned system of equation. In fact, the coefficient matrix that we have seen here, if you look at this, it is called a Hilbert matrix actually. If you see these coefficients 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 3, 1 by 4, 1 by. So, you go 1 by 4, 1 by 5, 1 by 6, and that matrix is for very high values, this matrix is an ill conditioned matrix. Therefore, that is the reason why it becomes a ill conditioned system of equations, and we do not use very high order approximations taking as polynomials. But in practice, normally in the engineering applications, one probably do not go beyond even a cubic approximation. I mean, given a data of points that is given, you may not like to go beyond a cubic polynomial to be fitted. In that case, you are safe, you can use the polynomial approximation. But if you use the orthogonal polynomials, we can do both the Legendre as well as the Chebyshev polynomials. You can still go higher order in this case, and you can have a better approximation in the sense the minimized error will be smaller and smaller as we increase the order of the approximation. Now, the least square approximation was obtained by using the Euclidean norm. Now, if I use the other norm, that is a maximum norm, uniform norm, then I get a different type of approximation, and that approximation we call it as a uniform approximation. We call this as uniform approximation. And this approximation is also called, it has another name, it is called the minimax approximation. It is also called the minimax approximation, and it is also sometimes called approximation in the Chebyshev sense. Why it is so, we will just see it. It is also called approximation in Chebyshev sense. Now, here we are using the norm that we are using is the maximum norm, we are using the maximum norm here. Now, let us define what is this uniform approximation. Now, we have a continuous function given to us. So, let us take, let f x be a continuous function, be continuous on a b, and let us write down our approximation. F x is equal to p n x is equal to c naught plus c 1 x c n x to the power of n. Now, let us write down the what is the error. The magnitude of the error will be equal to e suffix n to denote the degree of the polynomial approximation, and that is equal to f x minus p n of x. Let us review what is the least square approximation. We applied the principle that the aggregate of the sum of squares of the errors must be a minimum. In uniform approximation, we shall require that the maximum of the error, we are talking of all local maxima, which may occur at a number of points in the interval a b, and the minimum of the error, again we are talking of the local minima, which may also occur at a number of points in the interval a b, must be equal in magnitude. Further, this is very important, we shall also require that the maximum and minimum errors, which are of equal magnitude, must occur alternatingly. We call this approximation also as the minimax polynomial approximation. Therefore, the minimax polynomial approximation is defined by maximum of magnitude E n, which is a function of f c naught, c 1, c 2, c n, x lying in the interval a to b is equal to minimum of E n f c naught, c 1, c 2, c n, again x lying in the interval a and b. What does this imply? It implies that all local maxima and local minima are equal in magnitude. All local maxima and local minima are equal in magnitude. Now, let us first consider a very simple example to illustrate the uniform approximation. So, let us call it as an example. Approximate f x by a constant c naught where a is less than or equal to x, less than or equal to b. Here n is equal to 0. Now, we are talking of n is equal to 0, therefore, we simply have p n p 0 x is equal to c 0, p 0 x is equal to c 0. Now, since we are approximating f x by the constant c naught, c naught should lie between the maximum and minimum values of f x. Therefore, c naught lies between let us call it as capital M, the maximum value of f x in the interval a b, and the minimum value by small m of f x. Therefore, the value of c naught that we are talking of should lie between these two values. Now, to understand it, let us first draw the graph of the function f x. The function f x that is given to us, let us draw its graph. So, let us say draw the graph of f x. Let us take this point as a and let us take this as point b. We are approximating by y is equal to c naught. The maximum is this is capital M, the minimum is this is our small m, and the error is now m minus c naught. Notice that the graph is below the x axis, therefore, m is a negative quantity and therefore, the error would be this whole thing is the error and therefore, this will be minus m plus c naught. Now, we are requiring that errors in magnitude are equal, which would imply that m minus c naught and minus small m plus c naught, they must be equal. Now, both are positive quantities. So, I will not write the magnitude. M minus c naught is equal to minus m plus c naught, or 2 c naught is equal to m plus m. Therefore, c naught is equal to m plus m by 2. Therefore, our uniform approximation is f x is approximately equal to p 0 x is equal to c 0 is equal to m plus m by 2. Now, if this is the approximation to our function f x in the interval a b, let us try to find out the error. What is the error we have committed here? Now, the error would be this is the error, this is the error, we have made them equal. Therefore, I can find out the error either from this or from this. So, let us see what will be the in both the cases. So, I can now write this as m minus c naught is m minus m plus m by 2, that is m minus m by 2, or I can also look at this quantity, that is minus m plus c naught, that is minus m plus m by 2, that is equal to m minus m by 2. Obviously, both these errors have to be equal, because that is what the condition that we have put here, errors are equal. Therefore, it is sufficient for us to use any one of these points to find out what is the error that we have committed in this particular approximation. Now, it is not necessary that the graph of the function should be like this, the graph could be above the x axis also. Let us see what would happen in that case. Let us draw the graph. this is the point our A, this is the point B, this is our M, this is our small m, and this is the approximation that we are talking of y is equal to C naught. Now, the error would be m minus C naught over here, and the error will be this quantity, the error will be this quantity, and this quantity will be equal to C 0 minus m. This is our C 0 minus m, this will be the error C 0 minus m. Now, the magnitude of the errors are equal, therefore, I will again get m minus C naught is equal to C naught by m, therefore, I will get 2 C naught is m plus m, thereby giving us the same value for C naught, that is m plus m by 2. Therefore, this result would be the same whether we would take the graph cutting the x axis or it does not cut the axis. That means, this result is independent of the function that we are now choosing. Now, let us consider a linear approximation. Now, in this case n is equal to 1, therefore, I want to approximate f x by p 1 x is equal to C naught plus C 1 x, and error is epsilon x is f x minus p 1 x, that is equal to f x minus C naught plus C 1 x. Therefore, the magnitude of the error is equal to magnitude of f x minus C naught plus C 1 x is magnitude of E 1 f C naught C 1. This is a function of f and the two parameters that we have here C naught and C 1. Now, what is it that we shall require? We shall require that the maximum of E 1 should be equal to minimum of E 1. Therefore, we shall say we require maximum x lying between A and B of magnitude of E 1 is equal to minimum A less than or equal to x less than or equal to B of E 1. Furthermore, you remember that we mentioned that uniform approximation we shall require that the error should also alternate in sign. To do that, we would choose 3 points. Let us call them x 1, x 2, x 3, such that A is equal to x 1 less than x 2 less than x 3 is equal to B. That means, out of the 3 points, the first point is the starting point of the interval A, the last point is the end point of the interval B, and we need to determine x 2 also, x 2 will be an unknown. Now, error is at these points will be epsilon at x I is equal to f at x I minus C naught plus C 1 of x I. Now, this error will be either it will be plus E 1 or it will be minus E 1 depending on graph that we have there. Now, in order to have a understanding of what we see by plus E 1 or minus E 1, let us draw the graph of the error function, that is we are talking the graph of epsilon x is equal to f x minus p 1 x. Let us draw its graph. So, we are talking of the graph of epsilon x. We take this point as A, that is equal to x 1. We take this point as B, that is your x 3. Now, I will choose this point as x 2. Now, we are saying that this value is E 1, this value is minus E 1, this value is E 1. Therefore, the error is equal in magnitude, but the errors alternate in sign. This is E 1 minus E 1 and this is plus E 1. However, it is not necessary that the graph should be like this. We can also take graph like this. I can have this point as A, this will be my x 2 and this will be my B. In this case, it will be minus E 1, this will be E 1, this will be minus E 1. So, but it has to alternate in sign, that is all. For example, if the error was say of magnitude 0.5, then it could be either 0.5 minus 0.5, 0.5 or it could be minus 0.5 plus 0.5 and minus 0.5. Now, with this observation, let us now write down the requirement in the mathematical terms. What do you mean by this mathematically? Now, what we are writing here is that error at x 1 is equal to minus error at x 2. The error at this point and the error at this point, they are of opposite signs. Therefore, I will set error at x 1 is equal to minus error at x 2. That means, epsilon x 1 is equal to minus epsilon x 2, or I can take it to this side also and write epsilon x 1 plus epsilon x 2 is equal to 0. Now, since x 1 is equal to A, I can also write this as epsilon A plus epsilon x 2 is equal to 0. Let us number it as 1. Now, if you go to the next points, error at x 2 and error at x 3, they are of opposite signs. Therefore, I can again write error at x 2 is minus error at x 3 or error at x 2 plus error at x 3 is equal to 0. X 3 is the point B, therefore, I can substitute for B. Therefore, I will have epsilon x 2 plus epsilon B is equal to 0. Let us number it as 2. Now, we know that the given function f x is continuous. So, f x is continuous. Therefore, our error which we have defined here as f x minus p 1 x, p 1 x is a polynomial, therefore, p 1 is continuous, therefore, epsilon x is also continuous. Therefore, epsilon x is continuous. Furthermore, we have taken that f is differentiable also, therefore, epsilon also is differentiable. Therefore, we have epsilon x is differentiable. We are talking of our interval a b, so I can include that. Furthermore, we also have that epsilon at x 1 is equal to E 1 is equal to epsilon at x 3. Now, what we are talking of is this particular graph. Epsilon at x 1 is E 1, epsilon at x 3 is E 1, or if you are having a graph like this, they are of negative sign. Therefore, or we will have epsilon at x 1 is equal to minus E 1 is equal to epsilon at x 3. Therefore, the errors at these 2 points are the same. Therefore, I have a function epsilon x which is continuous in the closed interval a b, differentiable in the open interval a b, and epsilon at x 1 is equal to epsilon at x 3. Therefore, epsilon x satisfies the requirements of the Rolle's theorem. Therefore, epsilon x satisfies the requirements of Rolle's theorem. Therefore, there exists a constant C contained in the interval a b such that epsilon dashed C is equal to 0. Now, it is at this particular stage we will bring in this point x 2 that we are talking of. Now, since the Rolle's theorem states that there exists a point C such that epsilon dash C is equal to 0, we shall choose this point C as our x 2. Therefore, we shall say choose x 2 is equal to C, which would imply epsilon dash at x 2 is equal to 0. I will take this as my third equation. Now, we have earlier two equations and this is our third equation, and we will like to solve these three equations. Now, we have the equation 1 as epsilon a plus epsilon x 2 is 0. Let us write them all at the same place. Epsilon a plus epsilon x 2 is equal to 0, then epsilon x 2 plus epsilon b is equal to 0, and the third equation is here. Now, let us see what are the number of unknowns that we have in our problem. The unknowns that we have in our problem are, we have to determine C 0 and C 1, and we have also determined x 2. Therefore, we have got 3 unknowns in our problem. And what is the number of equations that we have here? We have 3 equations. Therefore, we have equations, 3 equations. Therefore, I can solve the system of 3 equations in 3 unknowns C 0, C 1 and x 2. However, these 3 equations are nonlinear equations. These are nonlinear equations. However, if I solve them in a systematic way, we will say what is that systematic way, we will just see it later. Then it is very easy for us to solve even these nonlinear equations. For example, one equation that would really help us is that if I subtract 2 and 1, that is 2 minus 1, then I get here epsilon b minus epsilon a is equal to 0. So, I get epsilon b minus epsilon a is equal to 0, and this does not contain x 2. Therefore, the work will be reduced by using such an equation. Now, how we shall use it, we will see later on in our next lecture. We will do a problem on it and see how we are going to apply this particular thing. We will close it for tonight.